Hi, my name is Bahadur Ahmedov. In this video lecture, we are going to discuss about precise definition of limits. If you remember in our previous lecture, we found the limits by getting the values of the x closer and closer to the a and finding the limit of the function. So especially we talk about this function and we've seen that sine of x over x comes very close to 1 or is equal to the 1 as x comes closer to the 0. And we define this limit as sine of x divided to the x gets closer to 1 as x gets closer to 0, right? And the only thing which we need to talk is say this words closer and closer. So how much x should come closer to the 0 so sine of x divided to the x gets closer to the 1. This is the question which we would like to address and which we would like to answer. Say how much closer x should get to 0 so that sine of x divided to the x gets closer to 1. So in order to motivate the precise definition of the limits, so let's consider another function. So I'm going to write down the function f of x is equal to, so 2x minus 1 if x is not equal to the 3, and it is equal to the 6 if x is equal to the 3, right? So we can see here that if you take the values of the x like close enough to the 3, like 2.999, like a 2.9999, and so on, close enough to the 3, the value of the function becomes very much close enough to the 5, right? So, and the only question is, so how much x should be close to the 3 so that f of x is going to be close to the 5 in the distance of, for example, 0.1. So let me write this down, this question. So how much or how close to 3 does x have to be so that the distance between f of x and 5 is smaller than 0.1, right? So we would like to control the distance between f of x and 5, and by controlling the distance of the x and 3. So this is our goal. So I would like to write this down in this way. So the distance between f of x and 5 is smaller than 0.1 can be written as f of x minus 5 in its absolute value is smaller than 0.1 if x minus 3 is smaller than the delta, right? So this letter is the Greek delta from the Greek. So I would like to control this. So if I just control this delta, if I take this small enough, is it possible that f of x is coming very close to the 0.1, is f of x is coming very close to the 5? Well, I would like to find exact value of this delta. So please notice that if x minus 3 is becoming closer, so if x becomes closer to the 3 in a distance smaller than 0.05, then f of x is becoming closer to the 5 in a distance smaller than 0.1. So how we can show this? So if you remember, the value of the function f of x is equal to the 2x minus 1, right? And I'm just going to put this into here. So the 2x minus 1 minus 5 in the module should be smaller than 0.1, right? So I'm going to make some simplifications inside the brackets, and it is going to be 2x minus 6 is smaller than 0.1. So if I take out the 2 out of the brackets, and what I have here is 2 times the x minus 3 is smaller than 0.1, right? And from here I can find that the x minus 3 should be smaller than 0.05, right? And it gives me the answer to my question. Like if I come closer to the 3 for the x smaller than 0.05, then f of x becomes closer to the 5 in a distance smaller than 0.1. And that's going to be the precise definition of the limits. So please note that these two distances are dependent. So by controlling this distance, delta, I can control this distance, which I'm going to denote as an epsilon. So let me write what I want to say. So the f of x minus 5 is smaller than 0.1 if x minus 3 is smaller than 0.05. But I can control this distance. If I would like to be closer to the 5 in a distance of 0.01, then we should choose the distance between x and 3 to be equal to 0.005. Or if I want that the distance between 5 and f of x is becoming smaller than 0.001, then we should choose the distance between x and 3 smaller than 0.005. So we call all of these numbers like 0.1, 0.01, 0.001 as an error tolerances. So we call these numbers as the error tolerance. So if we come closer to the x, we can control the proximity level of the f of x to its limit. So in general, we can write this down as f of x minus 5 is smaller than epsilon if we choose the values of the x close enough to the 3 in a distance of the distance. And in our case, this distance is equal to the epsilon over 2. Okay, so the main goal here is to write down the dependency of this epsilon and this delta, and we found this relationship. The relationship between these two distances is epsilon over 2. So let's go back to our first definition of the limits. Do you remember here that sine of x gets closer to the 1 as x closer to the 0, right? So now we have defined it, we have figured out how much close the x should get to the 0 so that the sine of x comes to closer to the 1, right? So if you know this distance, this epsilon, then this distance should be equal to the epsilon over 2. So if I choose the x close enough to the 0 in the distance of epsilon over 2, then sine of x over x becomes very much closer to the epsilon. Okay, so of course, depending on the function, this relationship between this distance and this distance might be different. So in our example, it was epsilon over 2, but in general, this might be different. So that's going to be the precise definition of the limit, and I'm going to define this. So let us write this down, the definition. So let f be a function defined in an open interval. Function defined in an open interval containing the number a. The number a. So then we say that the limit of f of x as x approaches to is equal to L as x approaches to a, as x approaches a, and we're going to denote this in the form of limit of f of x is equal to the L as x approaches to the A if for every number, so for every number epsilon, which is more than 0, there exists the delta, which is more than 0, such that if I choose the distance between x minus a and the distance of the delta, then f of x becomes closer to the L in the distance of epsilon. So I'm going to write here, so this letter is called the epsilon. Again, this is the Greek letter. So this definition basically tells me that the limit of f of x is equal to the L as x approaches the A means that I can control the distance between f of x and L. This is the distance between them by controlling the distance between x and A. So there should be always the dependency between these two distances. This is essentially what does this definition mean. So let's do an example. So how we can do this. So usually we are not going to use this definition in order to find the limits. So usually we use this definition in order to prove the existence of the limits or prove the limits. So let's try to do some exercise. So prove that the limit of 4x minus 5 is equal to the 7 as x approaches the 3. So we are going to follow always the two steps in order to do this. So in the first step, we are going to make like preliminary analysis, by just guessing the values of the delta and epsilon. So by just finding the relationship between the epsilon and the delta. So if you remember the precise definition of the limit, it tells you that if x minus 3, right? So the x comes to closer to the 3 and a distance smaller than the delta, then 4x minus 5 should come closer to the 7 in a distance smaller than epsilon. So what I want is, I would like to simplify this expression. So let us do this. 4x minus 5 minus 7 in the model is equal to, so 4x minus 12 in its absolute value. So we can take out the 4 out of the brackets. And if you do this, what we get is 4 times is x minus 3. Yes, so it should be smaller than the delta. Okay, so it is clear that so if x minus 3 is smaller than the delta, then so the x minus the x minus 3 should be smaller than epsilon over 4, right? So this x minus 3 smaller than epsilon is, over 4 is not about the limit of the x, right? It's actually the limit of the function itself, closer to the 7. We just simplified this expression and we wrote this here. So look at these two expressions at here, for example, and at here. So they are the same expressions, but the second term here is just simplified version of the one which is above. So it gives us some insights that if I choose the delta to be equal to the epsilon over 4, then I can control this distance. So this is the first step when we are going to figure out this relationship between the delta and the epsilon. And in the second step, we are going to prove or show that this distance delta works. Show the delta works. So in this case, what I need to do is I need to put that, hey, if x minus 3 is smaller than delta, which is equal to the epsilon over 4, then 4x minus 5 minus 7 is going to be smaller than the epsilon. And it works because I can substitute this delta over 4 or like epsilon over 4 into here and show that, hey, so the 4x minus 5 minus 7 is going to be equal to the 4 times to the x minus 3, right? So I know that this is going to be smaller than delta. 4 times is the delta. At the same time, I know that the delta is equal to the epsilon over 4, so it is going to be equal to the 4 times the epsilon over 4, which is equal to the epsilon. So this expression is smaller than epsilon if I choose that x minus 3 smaller than delta, which is equivalent to the epsilon over 4. So this is a little bit theoretical, but this shows, so it proves us what we want. So if we get closer to the 3 for the x, so our function gets closer to the 7. So we can show this graphically as well. So let's try to sketch the graph of this function and try to understand what does this limit expressions mean. So our function looks like roughly like this. And when x is equal to the 3 actually, so it becomes very close to the 7. So when x is equal to the 3, it becomes very close to the 7. So what we are doing is, so this is 3 here on the x-axis. So this is the x-axis, this is the y-axis. This function here is 4x minus 5. Y is equal to the 4x minus 5. So if we control the distance for the x, for example, if I just control this distance here, okay, so it is going to be 3 minus delta, and here this is going to be 3 plus delta, where the delta is equal to the epsilon over 4, then our function's value is going to be within the distance of the epsilon to the 7. So here it is going to be this distance, it is going to be 7 minus epsilon, 7 plus epsilon. So this is what we call as a precise definition of the limit. So essentially, I can choose the distance between the three. So I can choose this distance. This is the delta, so that I can control this distance here, the epsilon. And I know that the relationship that I need to choose the epsilon to be equal to the epsilon over 4 in order to choose this. So again, so if you want that your function becomes very much close to the 7, for example, in the distance of 0.1, then you need to choose the delta, so the distance to the x. Then you need to come closer to the 3 at the distance of smaller than epsilon over 4, 0.1 divided to the 4, in order to get that value. Okay, again, if you remember, when we used to do this kind of things in a previous lecture, we just chose the values of the x, right? So x used to be equal to the, like, if you would like to find the limit of this function, the limit of the 4x minus 5 as x comes to the closer to the 3 is equal to the 7, for example. What we did is we chose the value of the x to be equal to the 2.1, 2.5, then 2.9, then 2.99, and so on. So we chose the values of the x closer and closer to the 3 in order to see how much, what is going to be the value of this function, right? And this definition now gives you some insights about how much you should come closer to the 3 so that this 4x minus 5 comes close enough to the 7. So it tells you that, hey, if you want that this distance is going to be equal to 0.1, then I should continue here until 2 point, so 3 minus 2, 0.1 minus 4. Okay, so, but we know that sometimes limits don't exist. So sometimes the limit of the function goes to the infinity, and we need to also define this case, so how to prove that the limit of the function does not exist. So we are going to make another definition for this case. Definition. So if the limit of the f of x is equal to infinity, so x goes to the a, means, so this limit means that for every positive number, for every positive number m, there is a positive number delta such that if this distance x minus a is smaller than the delta, then f of x is more than m. So do you remember in our previous examples, or in a previous definition, the f of x should be closer to the L, right? And now we just need to show that. So I can always find this m so that my function is going to be even bigger that m if I just control the distance of the x into the delta. So let me show theoretical example. So this is going to be an example of the limit of 1 over x in the square. So as x approaches to the 0, it is going to be equal to the infinity. And then we're going to illustrate this and try to understand what does it mean. So essentially it means that so you can always figure out the value of 1 over x in the square bigger than any constant you choose, m, by just getting this x closer and closer to the 0. So I'm going to show it to you. So again, if x is closer to the delta, then 1 over x in the square is more than m. So this is what I need to show. Okay? So, but at the same time, I know that 1 over x in the square is more than m. It means that x in the square is smaller than 1 over m. So I'm just going to take the reciprocals from both of the sides. So that is why this this greater sign is going to change to the smaller sign. So at the same time, we can write this down as the absolute value of the x is smaller than 1 divided to the module of the, so the square root of the m, sorry. So if we choose delta to be equal to the 1 divided to the square root of m, then um, then if I can choose the x closer to the 0 at the distance of the delta, which is equal to the 1 over square root of m, then 1 divided to the x in the square is always going to be bigger than m, right? So we just shown this here, and this is true because if you just like substitute this to here, it is always going to be greater than m. So graphically, it basically it looks like this. So I'm going to sketch the graph of this function. So approximately, this function is going to look like this. So I'm just going to try to explain you what does it mean. So you see, so this function is becoming really, really big as I'm approaching this point A, right? As you approach the A from the right or from the left for the values of the x, this function's value is becoming really a lot. And here, what you are doing is, so if you just control this distance around the A, for example, by just choosing this like this, so let me put the A to here in the middle. So if you control the distance around the A, so big enough, or so by just controlling this distance, it is going to be the A plus delta and A minus the delta. So it's actually A minus or x minus A smaller than the delta. So this is all of the values of the x within this interval. Then the value of the function is becoming greater than this value of the m. So I'm just going to show this. So this line is going to be m. But again, so you can see here that you can always get this x closer and close. So you can always control this value of the m. So if I want that my function's value is becoming even bigger than this m, for example, this m, then I can still do this by controlling the distance, right, around the a. So I can just take this delta even smaller, right, like this. And in this case, the value of the function is becoming even closer, even bigger than the m. So this is what is the meaning of the infinity limit. So you can always figure out the value for the delta so that your function's value is becoming greater than any m you choose. So here are the two examples which we use or which demonstrate how we need to prove the limits of the functions when the limit is finite and when the limit is infinite. So thank you very much for your attention. I hope that this was helpful for you.